Hi everybody, I want to show you a software that I built called RIS-Kernel to bypass memory limitations on running LLM on local machines with no GPU capacity. I will start the process because it will take a few seconds. Meanwhile, I will explain what I did. Here I have a script showing the machine's capacity. After I run this script, you can see that I'm using a machine with 15 gigabytes, a very old processor, a few cores, and no GPU detected. On a standard CPU with 16 gigabytes of RAM and no GPU, we processed 18,000 tokens using the RIS-Kernel. Think about this amount of tokens squared. With just 1% density and 70 seeds, we bypassed a 40 gigabyte allocation, compressing the context into a 518 megabyte cache loaded in 22 seconds. Next, watch the RIS model directly answer some of the most skeptical questions about its own design. I will let the RIS-Kernel defend itself against skeptical people. Enjoy.
User language is highly structured and sequential. Why does uniform random sampling succeed in retrieving facts? Wouldn't dropping 99% of your attention connections at random break grammar and semantic coherence? Assistant random sampling, such as the one used in RIS-Kernel's stochastic mode, can still effectively retrieve factual information because it maintains a global view of the sequence while discarding local details. In the context of retrieval tasks, where the goal is to find specific pieces of information rather than understanding the entire context, this approach works well. The randomness helps ensure that each token has an equal chance of being selected as a neighbor, which is crucial for maintaining the integrity of the graph structure. The key insight here is that even though you are randomly selecting tokens from the complete set, the probability distribution ensures that important nodes, hubs, have higher chances of being sampled. This probabilistic approach allows the model to maintain some level of contextual relevance even when only a small fraction of the full attention matrix is retained. User, you showed that Tiny Llama collapsed completely beyond 4 times its native context limit even with yarn scaling, while Qwen-2 scaled successfully to 64,000 tokens. Does this mean your method is highly dependent on the host model's native training? Assistant, RIS-Kernel is designed to be flexible and adaptable across different models and contexts. The key aspects of RIS-Kernel are 1. Stochastic sampling. It uses a probabilistic approach to select global neighbors for each pivot in the sequence, ensuring that high-importance routing pathways are maintained. The ability of RIS-Kernel to scale effectively depends on several factors. Host model design. The architecture of the host model, e.g., Llama, Qwen, plays a crucial role in determining how well the system can handle increased context lengths without collapsing. For instance, when using the yarn scaling scheme, which scales attention density linearly with token length, the model performs better up to a certain point before it starts to collapse. This suggests that there might be an inherent limitation in the host model's positional encoding or other parameters that affect retrieval performance at very low densities. Future work. To improve robustness and scalability, future work could include extending the sampling strategy to weighted networks and directed graphs, as well as exploring more sophisticated ensemble methods like deep ensembles or Bayesian optimization to further enhance performance. User, how does your pre-fusion unified softmax prevent token dilution compared to traditional sparse attention approaches? Assistant, the dynamic rope scaling in PFUS, parametric fused unification softmax, techniques in RIS-Kernel are designed to address the limitations of traditional sparse attention methods by ensuring that all tokens contribute equally to the softmax computation. This is achieved through a unified soft fusion approach where both dense and sparse components are processed together, rather than separately as in previous methods like Longformer or BigBird. This unified softmax ensures that each recovered token competes with other tokens in the ensemble for retrieval opportunities, thereby reducing bias towards certain tokens over others. This method helps ensure that the model's output remains coherent and relevant even when only partial information is available.